Welcome to the Problem Channel Season 3, Episode 44, the episode which I titled A Story of an All-of-One Bucket List, because in this episode we will discuss the design process of a practically useful big O of one-time complexity algorithm. But before we deep dive into the details of the relevant computer science, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit for yourself from working with the material that we present on this channel is for you to go to the homepage of our channel, and at the top of that page in the channel's trailer section, find the episode titled The Problem Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. And in a lightning round on this channel, we solve problems in mathematics, physics, and computer science in a happy and a never-ending chain. If you have any questions, then by all means do ask. The best way to ask your question is to find an episode on our channel that resonates with you and use the comment section under that episode, and I will take it from there. And of course, and as usual, I would like to extend my deepest gratitude to all the current supporters and the current subscribers of our channel, especially the people whom I know personally from Quora. Thank you very much for your support and your practically useful suggestions. And as one final small announcement, because lately I'm asked on a regular basis, how do I use this channel? In addition to the video material that I put together that answers this question, I also put together a written document that answers precisely that question: how do I use this channel to maximize my own benefit? That document is called How To. The link to that document, a free PDF file, is in the comment section to this episode. And as a final note, this document will be helpful for both the newcomers and the veterans of our channel alike, because it gives you a very nice and succinct 1,000-foot view of this channel in one convenient document. The objective of the computer science problem S3CS10 was to design a practically useful big O of one-time complexity algorithm. And because one of the main messages that I'm trying to propagate on this channel is the fact that mathematics fundamentally is an art form, and mathematics is a foundation of both theoretical physics and computer science, it follows that both theoretical physics and computer science are also forms of art, and the art of telling a story. Now, in slightly more details, the veterans of this channel already know that mathematics is an art of telling a story. Mathematics is an art of telling a story of how and why. Mathematics is an art of telling a story of how and why wrapped into a technical language of if P then Q implications, the universal quantifier for all, the existential quantifier there exists, and the logical connectives and not or, in its very dry, pedantic, and technical description. But theoretical physics is its own highly specialized applied mathematics, let's say, and computer science as well is its own highly specialized applied mathematics. And again, for that reason, both theoretical physics is an art of telling a story and computer science is an art of telling a story, which means that, again, coming back to the way these things work, if you're not telling this specific story, then you are not doing computer science. And if you are telling a story, then it remains to be seen whether you are doing computer science or not. And because in general I do not talk about things that I do not have a first-hand experience with, as I explained it in season 1, episode 1, in the opening episode on this channel, the first episode ever, sometime in the past, I tried precisely that experience because I wanted to see for myself what is the parallel between, let's say, visual arts and the mathematical arts. I put a pen to a paper, a brush to a canvas, and I stuck my fingers into wet clay, and then my art instructor fired whatever I was able to come up with in a kiln, and voila, you have something that can be called, let's say, a sculpture. And as I showed you guys, season 1, episode 1, again, this is my study of a male torso. And again, you be the judge whether it looks like a male torso or not. This is a study of a male foot. Here it is. Again, you be the judge whether this looks like a male foot or not. This is another study of a female nude. Again, you be the judge whether it looks like a female nude or not. But the point is that in order to produce any worthy work of art, two things need to be present or exhibited by the author at the same time: the discipline of and the rigor of precision on the one hand, and the fluidity of improvisation on the other. Any one of these threads taken in isolation, the rigor by itself, or just the fluidity of an improvisation, will not result in a good thing. The two things must be combined, and these are exactly the same two things that we combine in mathematics. And if you think that achieving this precision and the rigor and the discipline of that precision is easy, then try to capture, I recommend as a useful exercise, try to capture your own likeness, let's say in clay or in graphite or in paint. Sit in front of a mirror, grab a piece of paper, grab a pen, and see if you can render your own likeness so that other people can say, oh yeah, look, this is exactly you. This is not exactly easy. And I still recommend that even if you think that it's not going to work, try it anyway. On the internet these days, you can find the famous drawing of a rooster by a famous theoretical physicist, Richard Feynman. So apparently a person like a theoretical physicist was not too bad at drawing. Again, you will never know until you try. And if you still think that this is not your cup of tea, I still recommend that you go to a museum and see how the masters of the past did their thing. And when you walk into a museum and look at the work of art, I suggest that you take a stance of a creator, meaning what would you feel, what would you think, how would you go about these things if you were to create that something by yourself with your own hands. And at some point you should be able to recognize this work of art. For example, please take a look. That is correct. It's not a bad idea to bring yourself up to a level when you can instantly say this is the statue of David by Michelangelo. And again, there's a word of caution and a fair warning: whenever you hear anything, not necessarily on the internets, anything from anyone, you should be skeptical, like any hard scientist should be. Once you start digging into the details of whatever you heard, it turns out that this is completely not true or only partially true. And again, depending on the setup of the whole information delivery, if someone or something is trying to push your emotional buttons, then most likely someone is trying to manipulate you for whatever reason. And if someone is pushing your intellectual button, then again, it remains to be seen whether that story is true or not. But this is where your brain comes in. You always validate the story by yourself. And the story that I know, again, to the best of my knowledge, please verify, the way Michelangelo actually crafted the statue that you just saw is nothing short of technically ingenious. Again, to the best of my knowledge, the way these things worked out in history in real time were as follows. Let's say Michelangelo was given roughly a chunk of marble that looked like a large brick. So it had a certain height, it had a certain width, and it had a certain depth to it. That was the chunk of marble. The objective is, from this chunk of marble, is to carve a statue of what later became known the statue of David. How do you do it? With the small to medium-sized statues, you can do it away by eye. That's not a problem. For example, the difference between working with clay is that the process is additive. You add the right amount of clay at the right place. Working with the marble, the process is subtractive. You remove the marble from the places where it should not be. You only leave the right amount of marble in the right place. So how do you do it with a very large, if not to say humongous sculpture. Well, this is where the technical ingenuity of Michelangelo came in. What he apparently did is he made a small, manageable copy of his future sculpture of David out of wax or paraffin, the material that's quite pliable and you can work it easily, small size. And then he made a vessel that looked like the same brick with the same proportions, which he then filled with water, into which he submerged the model, the smaller and more manageable model of his statue of David. And then he drained the water from the bottom of this thing little by little, so that once the water is drained, for example, let's say David's elbow is revealed to stick out above the water surface, and that little portion of marble was removed, keeping the elbow, the right amount of material in the right place. Once that was done, Michelangelo would drain a little bit more water and a little bit more water, exposing more and more of his model, and then he will be removing that much material from the actual marble that he was working with until he got the whole thing. And once you get the whole thing, he worked out the details. Obviously, that was not a problem. But if that is not your classical divide and conquer problem solving approach, then I do not know what is. And this can be spun in a number of different ways. Integral calculus, differential calculus in the works. So the point is that visual arts and technical ingenuity mix very, very well. And this is what we're exercising on this channel. And in this episode, we will also try to do the same thing as we apply our wits to the process of designing a practically useful big O of 1 time complexity algorithm. And to that end, we will, in this episode, this is our plan. First, we will set up the background into which we will embed the process of the design of a practically useful big O of 1 time complexity algorithm. Then we will go through 3 tries, 1, 2, 3. 3 is a charm. On try number 1, we will experience a miserable failure. On try number 2, we will fail again, but that failure will be better. It will hone us in onto a correct solution. On the try number 3, we will experience a success. Then we will look at a demonstration of how our algorithm works, and then we will look at some sample C code that I put together for you in 2 versions. The links to these files are in the description or in the comment section to this episode. Check where I put it. And without further ado, let's do it. Into a branch of computer science bank during its normal business operating hours, 9 to 5 or 9 to 3, whatever the case may be, through a single revolving door, meaning one customer at a time. Customers arrive at a completely random, unpredictable, and non-deterministic time. Once they walk into the bank, they acquire a shared resource, a pen, in order to fill out a certain paperwork. And the time that it takes for a randomly arrived customer to fill out his or her paperwork is also completely random, unpredictable, and non-deterministic. However, once that paperwork is complete, then the shared resource, the particular pen that the customer was using, is returned to the common pool. And at this point, the mathematically oriented thinkers know that we already have a bijection between the pens and the buckets in which these pens are located. That means that to each particular bucket there corresponds a certain pen, and conversely to each pen there corresponds a certain or a particular bucket. Our bucket can carry at most 1 pen at a time. Evidently, when the pen is taken by the customer, the bucket is empty, but when the pen is present in the bucket, then only 1 pen can be present in the bucket, and conversely, any given pen can be resting in only 1 specific bucket. And the way we establish this bijection is using the traditional mechanism of whole non-negative numbers. For example, we write 0 on the bucket, 0 on the pen, or 0 on the pen, 0 on the bucket. 1 on the bucket, 1 on the pen, 2 on the pen, 2 on the bucket, and so on. So that means that at any point in time, The customer who uses a shared resource, a pen, while the corresponding bucket is empty, knows exactly which bucket this pen belongs to. So again, any bucket can be in only two mutually exclusive states. It either has exactly one pen, no more, or zero pens, no pens. And while the pen is used, of course, the customer uses one pen. This bucket is empty, but then once the pen is returned, it can be put into only one bucket. And the buckets are aligned, let's say, by the entrance into the branch of this computer science bank by the entrance in a tight formation with no gaps and no overlaps. And once this background information is understood, the key requirement for the upcoming design of the algorithm is the following. The shared resources depends. They must honor or obey these two requirements, both the acquisition time or request for a shared resource and the amount of time during which this shared resource is used, or the time when the resource is released, are completely random, unpredictable, and non-deterministic. And that means that for the purposes of this episode, we agree that for the purposes of designing this specific practically useful big O of one-time complexity algorithm, there does not exist a computer science or otherwise a mathematical algorithm that can predict with absolute certainty, the time when the customers walk into our computer science bank and the time when that means that the time when they grab a pen and the time when they bring this pen back. Under these conditions, our objective, the whole purpose of this mission, should you choose to accept it, is to design a computer science data structure and the corresponding computer science algorithm that will allow our customers of our bank in the given setup to grab a pen and return a pen to a bucket once they're done with their paperwork in big O of one-time complexity. Once the problem statement is understood, pretty much all the students who take on this problem realize right away that our tight partitioning of the tables and the buckets with the pens on them with no gaps and no overlaps are a model of what classical computer science structure. An array, exactly, and an array characterized by specifically these two features, equally sized, contiguously placed chunks of memory, and this is what we have, equally sized, contiguously placed objects. And in a classical array, if you take away any one of these requirements, then the classical array dissipates and stops being a classical array. If we start varying the size of the chunks that we contiguously stick next to each other, it is not a classical array. Or even if we take the same size chunks but break them apart and place them at random memory locations, it also stops being an array and becomes a linked list or a tree or some other perhaps wild structure. But in this case, we have a beautiful setup, equally sized, elements partitioned tight next to each other with no gaps and no overlaps. So we technically have a model of a classical computer science array. And at this point, the idea that visits most or pretty much all students who take on this problem is the following. Basically, it comes out to a linear scan of an array. Why don't we, on our first try, make our customers walk along the table of buckets and pens with them and basically look for the first non-empty bucket. The moment the customer sees the first non-empty bucket, aha, this is my pen, grab a pen, go do the paperwork, and once the paperwork is done, go bring it back. Now, it is important to understand as a technical wrinkle, so that once the pen is acquired by a customer, the customer knows which bucket this pen belongs to. So in some sense, the customer can simply return the pen to its bucket and walk away. So the returning of a shared resource at this time is done in big O of one time complexity requirement, and this is precisely what we want. However, a linear scan of an array, when the customers are forced to walk all the way across the set of tables and buckets and pans, carries what time complexity? Carries the time complexity of big O of n. For example, in the worst case, we will have to walk the entire set of tables all the way to the last table or all the way to the last element in the array, visiting each one in return, only to discover that there are no more shared resources left. All the buckets are empty. The last bucket is empty. There are no pens. So now we're either blocked or we'll have to go do something else. But in this case, again, the overall time complexity for a linear scan is big O of n. Big O of n is definitely not big O of 1. So this try is a failure, which is expected to happen. With a minuscule intellectual effort comes a poor result. Doesn't really matter where this scenario unfolds. Computer science, theoretical physics, or mathematics. This is how these things usually work. Little effort and poor result. But it is perfectly fine because remember, one more time, hopefully you're beginning to understand that solving a problem in computer science is isomorphic to solving a problem in theoretical physics, which is isomorphic to solving the process of solving a problem in mathematics, which is isomorphic to the process of coming up with a worthy and interesting work of art. It is a process, iterative process, during which a failure is not just an option, it is pretty much a guarantee. We will try and fail several times, and whether someone is able to persevere and walk through the failures will determine or will separate those who can from those who cannot. And in this case, that means that we need to try harder and we need to come up with something. We need to introduce the disturbance into force, so to speak, in order to come up with a practically useful computer science algorithm, in this case, that will allow our customers, instead of walking down the aisle, so to speak, in big O of time, big O of n time complexity, grab the pen in big O of 1 time. All the viewers of our channel should understand well that computer science and computer programming are two very distinct endeavors, and that means that a particular person can be an outstanding computer scientist but a very lousy computer programmer, and conversely, a person could be an awesome computer programmer but a very lousy programmer. But there is one area where both computer science and computer programming intersect, and that area is called in general and known as a debugging process, or the process of figuring out what is wrong with this code or what is wrong with this idea. So bringing this idea into front and center situation, if we go back to our previous attempt where we failed miserably to come up with an algorithm that satisfies the requirement, why did we fail? Well, we failed because there was no permanent storage of the address of the first non-empty bucket. And how can we fix this problem once we understand what the problem is? And remember that if you understand what the problem is, you may or may not be able to figure out how to fix it, but understanding what the problem with your code or with the design is a necessary, it's not sufficient, but it is a necessary requirement for a success. So here we understood that we need to permanently store the address of the very first or minimally numbered non-empty bucket with our bucket list, because then our customers will be able to walk into the computer science bank through a revolving door, look at the number on the board, and access or be able to grab a pen in big O of 1 time, walk to that bucket right away without the linear scan. So here on this board, by the beginning of this set of tables, buckets, and pens, we put that number, and the meaning of that number is what? The meaning of that number is the following: the address of the first non-empty bucket, the bucket that has a pen in it. So how will this idea work in practice? That means that in the wee hours of the morning, a clerk of our bank will set up the tables, the buckets, they put the pens into the buckets, number the buckets with the early consecutive whole non-negative numbers 0, 1, 2, 3, 4, 5, 6, 7, and so on. And that clerk will put which number on the board to prime our algorithm. The clerk will put big fat 0 on the board by the beginning of our set of tables. The first customer at the bank opens its doors for business. The first customer walks in, sees the number 0. In big O of 1 time, the customer walks to that bucket to that table without the linear scan, grabs the pen from here, and then here is a wrinkle. Those of our viewers who studied a little bit of the theory of numbers, they know that in the theory of numbers, we have this notion called John von Neumann's successor function. So the successor of 0 will be what? 1. So the person who grabbed that pen from the bucket 0 will erase this number, put the number 1 on the board, and go on his or her merry way to fill out the paperwork. The second customer walks through the door, sees the number 1 on the board, knows that the bucket number 1 is the first one that is not empty, walks to that bucket in big O of 1 time instantly without the scan, grabs the pen, erases the number, puts the successor of 1, which is 2, and goes on to fill out the paperwork. The next customer walks in, reads the number on the board, it's 2 in big O of 1 time. That customer grabs the pen, erases the number 2 before he or she walks away, puts what? Puts the number 3 on the board, and so on things go. So at this point, with the introduction of this one element, this is our mock debugging session, we understood what was the problem with our original design, and now we came up with a way to guarantee that our customers can grab a pen in big O of 1 time, or so we think. So now we try to play out our algorithm and see if it has any chance to work. Amazingly enough, it actually does, provided or under a condition that our customers, again, knowingly or unknowingly, use our bucket list as a computer science structure called a stack or a last in, first out fashion. And what does that mean? That means that the times that our customers took to fill out their paperwork is highly orchestrated. In other words, in this case, our customer number 2 is the first one to fill out the paperwork. He or she returns the pen to the bucket number 2, and before he or she goes away, what number will he or she write? She will write number 2, meaning that the bucket number 2 now contains the pen. Now, after that, look at this carefully. No customers arrive. The customer number 1 finishes the paperwork, puts the pen in the bucket, erases number 2 on the list, meaning that the first non-empty bucket is now 1. And again, no new customers come in. The customer number 0 is done with the paperwork, puts down 1, erases this number. As we shall see, this is pretty much a futile exercise, but it so happens, puts 0, and on it goes. If customers use this particular bucket list precisely in a stack or last in first out fashion, 0, 1, 2, 3, 4, 5, 5, 4, 3, 2, 1, 0, then our algorithm seems to work. So theoretically, it is possible, but how practical is it? Well, it is completely not practical because remember the first 2 fundamental requirements for our design: the acquisition of a shared resource, or the time when the pen is grabbed, and the release of the shared resource, or the time when the customer is ready to bring the pen back to its bucket, are completely random, unpredictable, and non-deterministic. So how can we expose this weakness in the design of our algorithm? Well, let's play out this scenario again. The customer number is 0, 1, 2, 3, and 4 come in. They grab their pens, they go do their paperwork. I will not play out this scenario step by step. You understand every customer grabs and writes down the number. So what number should be on the board right now? That number should be 5, meaning that the smallest numbered bucket that is not empty or has a pen in it is number 5. Now, in a totally realistic way, let's say that the customer number 0, let's say, finished his or her paperwork. She or he knows where to put it in. So the customer puts the pen into this bucket. The customer erases the number 5 on our board, maintaining what? Maintaining the number of the first non-empty bucket. So what number goes on this board? Goes 0. Now at this point, our intermediate customers are still busy with their paperwork. At that point, a new customer walks through the door into the bank. The customer sees the number 0 on the board. Wonderful. In big O01 time, that customer grabs the pen, erases the number on the board. But the question is now, what number will this customer put on that board? And most interestingly, why? Once we understand what's going on with the answer to this question, we will understand or expose the weakness of our design. So here on the one hand, we can step into the world of probabilities and try to entertain the following idea. At that time, when the customer who grabbed the pen from the bucket number 0, and he or she has to put a number over here, which is the indication of which bucket number carries a pen in it, what is the level of certainty of this customer that the next bucket has the pen in it? Well, I would say it's not completely 0, but it's also not 100%. There's, if we carefully work out the numbers, it may so happen that there is a certain non-zero probability that the number can be 1, but what is the only way with absolute certainty to establish what is the actual number that should be here on the board? Well, the only practical way over here to produce a number of the lowest bucket that has a pen in it, non-empty bucket, is to do what? Again, engage in linear scan. The customer who grabbed the pen from the bucket number 0 has now to scan the entire list or the entire bucket list one by one and check, is there a pen? Is there a pen? Is there a pen? Is there a pen? No. Is there a pen? Oh yes, boom, number 5. And the customer can put number 5 on that list and go on his or her merry way to fill out the paperwork. But that step already kills our big O01 requirement for the acquisition of the pen, because before the customer can move on and use the shared resource, an effort of big O of n must be put in. And as we already understand, big O of n is not big O of 1. And that means that we need to figure out what is wrong with this particular design. As usual, if you want to maximize your own benefit from working with the material that we present on this channel, just like in physics and mathematics, we recommend that just about now you put this video on pause, walk away from the computer, and try to think on your own, why do we have a problem in our try number 2, and then compare your ideas to ours. But essentially, the reason why we have a problem with our second iteration of the design of this big O1 computer science algorithm is because the implicit linkage information that was inhaled into the bucket list by the clerk prior to the bank opening its doors for business is not permanently stored in that list. I wrote these things down for you because I realized that when information is written down, it is better perceived by students, and it is very important in this case to realize why we have a problem, because the implicit information is not stored with the list. Remember that we solved our first problem with the first iteration by doing precisely that, a permanent storage of the index of the first non-empty bucket with our bucket list. Here we solve this problem in a similar way, and not only that, but it is so important that I wrote it down for you in red. That information, or the knowledge of the first minimally numbered non-empty bucket in the list, constitutes the invariant of this particular data structure and of that particular algorithm. And once we realize that this linkage information is not permanently stored, once we realize what the problem is, now we can begin thinking about ways of fixing it. How can we fix this problem? Well, the way we fix this problem is the way in which, or a way in which many computer science problems, and not only computer science, but computer programming problems solved as well. And that's called indirection. In other words, we store the pointers to. We store the pointers to. In other words, the linking information that was implicitly inhaled into the list when things are nicely ordered and no one is using the list must be stored in the list permanently. In other words, at the bottom of every bucket or into every bucket, we put a piece of paper. We put a piece of paper, and this points to now no more pens. Into each and every bucket, we put a piece of paper, and on that piece of paper, initially, of course, we will write down the name of the next bucket. But the overall meaning of that list is to store the address of the first non-empty bucket, and that list will be maintained by the customer at the time when the customer returns the pen to a bucket. So now let's see how this will work in practice. In the wee hours of the morning, our favorite bank clerk arrives at the bank, sets up the tables tight with no gaps and overlaps, puts one bucket on each table, numbers these buckets with the early consecutive whole non-negative numbers 0, 1, 2, 3, 4, 5, 6, 7, and so on, puts one pen into each bucket, established as a bijection. Everything is wonderful. But now, in addition to these things that our clerk used to do before, now at the bottom of each bucket, the clerk puts a piece of paper on which he or she writes the number of the next, this is important to realize, the next non-empty bucket in this bucket list. Because this is a controlled environment of the initialization time, we know that the situation is as pleasant as it gets. We know that each next bucket carries the pen in it, so into each bucket starting from the first one, the clerk puts a piece of paper, and on that piece of paper he or she writes the number of the next bucket, because the next bucket carries a pen in it. So in the bucket number 0, at the bottom of the bucket number 0, there will be a piece of paper with the number 1 on it. So here there will be number 1. Let me perhaps write it with the with blue. So here at the bottom of the bucket number 0, there will be number 1. At the bottom of the bucket number 1 will be a piece of paper with what number on it? Number 2. At the bottom of the bucket number 2, there will be a piece of paper with what number on it? 3, because the bucket number 3 has a pen. At the bottom of the bucket number 3, there will be a piece of paper with which number on it? Number 4, number 5, number 6. And here there will be a piece of paper which says no more pens at this point. This will be a null pointer, so to speak. And once after that additional setup is done, the clerk puts the number 0 on the board in front of the set of tables or row of tables, and the bank is open for business. What will change now with our design? Because now we want to test it both. The ability of the customer to grab a pen can be done in big, is guaranteed to happen in big O of one time at all times, no matter how, no matter what the current state of the bucket list is. And the customer can return a pen into the bucket list in big O of one time in such a way that the next customer and the next customer and the next customer can acquire the pen from a bucket in the big O of one time with any intervening returns of the pens to their buckets in between in any which way, in unpredictable manner. So the way these things work now is as follows. When a customer walks into a bank, he or she reads the number on the sign. That number carries the address of the first non-empty bucket. Let's say in this case it's will be number 0. The customer walks to the bucket number blah, number 0 in big O of one time as demanded, grabs the pen from that bucket, but now instead of, remember, this implicit magic or implicit gains with von Neumann's successive function or implicit assumption that the next bucket in the list is the first non-empty bucket, what the customer do? The customer reads the number that is written at the bottom of that bucket and puts that number, not some hypothetically invented or a number that is grabbed out of thin blue air, but the number that is written at the bottom of the piece of paper of that bucket, the cheat sheet. So now the customer writes the number 1 on the board and goes on a happy, merry way to fill out the paperwork. Now let's say the next customer comes in, grabs the pen, reads the number on the board, grabs the pen in the big O of 1 time, and before walking away to fill out the paperwork, that customer reads the cheat sheet at the bottom of this bucket and puts that number, not some invented number, but puts that number that is now permanently maintained or permanently stored with the bucket list onto the board. This is the bucket number 2. And when the customer number 3 walks in, he or she reads the big number on the sign, walks into this bucket list in the big O 1 time, grabs the pen, looks at the cheat sheet. The cheat sheet says right now number 3. The customer erases number 2 on the board, puts the number 3, and walks away to fill out the paperwork. Now, let's say it so happened that, let's say the customer number 1 is done with the paperwork ahead of the customer number 0, and that customer returns the pen to the bucket. But now it is important that the sequence of steps to be understood well. What happens next? What happens next is the customer will read the number on the sign and copy that number onto the cheat sheet. So now the customer erases the number 2 that used to be on that cheat sheet and puts the number 3 in there. So now this link that used to point from 1 to 2 is broken. So now let's say technically this link will point to the bucket number 3, like so. This way it will point right here, because now the number 3 is over here. And once the customer is done with that process, so the number from the board on the return of the pen, the number from the board goes onto the cheat sheet on a piece of paper at the bottom of the bucket, but then the bucket number goes onto the board like this, the bucket number 1, and the customer walks away. But the first available bucket that is not empty with the pen in it is now number 1. So once that is understood, let us drill down into more details. Let's grab more pens and look at more realistic, let's say, random use of this particular bucket list. 1, 2, 3, 4, 5, 6. Now what we have over here essentially is a singly linked list pointing from bucket to bucket, but the memory store of this linked list or singly linked list is backed by an array. This is a wonderful hybrid, if you will, computer science structure, a linked list that is implemented inside an array, and every element of an array in plain English can be called a bucket, hence a bucket list. And a sure way to kill a joke is to begin explaining it is its punchline, but you now understand where did the title of this episode, a bucket list, came from. This is basically a linked list implemented backed by a set of buckets. So initially, let's say we'll look at a more detailed usage of this bucket list. Initially, our clerk set up the bucket list as I explained. The first customer walks through the door, and at that time the state of our bucket list is the following. The head of this list points to where? Points to the first entry, the first bucket. Bucket number 0 points to the bucket number 1. Bucket number 1 points to the bucket number 2, 2 to 3, 3 to 4, 5, 4 to 5, 5 to 6, 6 to null. No more pens, no more shared resources. At this point, the first customer walks to the particular bucket in the big O of 1 time as demanded, grabs the pen, and at this time we already know that before he or she walks away, the customer looks at the cheat sheet at the bottom of that bucket, and the cheat sheet at the bottom of this bucket says 1, and the meaning of that number is the index of the minimally numbered non-empty bucket. That number goes onto the board, and on it goes like this. Let's pretend again that the customer number 2 walked in, the same thing, customer number 2, 3 walked in, 4, 5, and almost all the pens are grabbed. It should be understood that if all the customers, the maximum number of customers come in, no more pens are grabbed, there will be null, or the sign no more pens, no more shared resources on the board. The next customer who arrives, depending again, this is, we can implement this as a blocking list where with the pthread mutex t and pthread condition t, when we can implement the blocking behavior on this list, or someone can asynchronously fail, go back and do something else. So let's say we have 2 more pens left. So which number at this point is on the board? Let's test your understanding of this algorithm. That's right, number 5 is on the board. And again, let us pretend that in random fashion, these customers are finishing their paperwork, no new customers arrive, and let us pick some inconvenient number. Let's say the customer who grabbed the bucket from number 3, for example, returned the pen. This is always a fun experiment to do in the live audience, where the members of the live audience tell the person like me which bucket now has the pen, what happened in this scenario, and we play it out. Let's say the customer who used the pen from the bucket number 3 is done with his or her paperwork. The customer puts the pen into the bucket number 3. What set of steps, what sequence of actions unfolds right now? Well, the customer looks at the bottom. Looks at the board and copies that number from the board onto the cheat sheet that goes onto the bottom of the bucket number 3. Since the number of the board is 5, the number on the board is 5, the number that goes onto the cheat sheet of this bucket, a pointer, becomes what? Becomes 5. So our pointers modeled with yellow arrows now go like this. From number 3, we point to number 5, like so. Remember again, this is important to understand. The number from the board goes onto the cheat sheet on the bottom of that bucket, and then the number of that bucket, once the customer is done with this manipulations, that number goes onto the board. Number 3 is the first, and this is actually true. The first non-empty bucket, the minimally numbered, is number 3. Let's say another inconvenient customer number is done with his or her paperwork. Let's say it's bucket number 1. Just to make sure it's not consecutive and we have some seemingly random pattern going on. So the customer number 1 walks to the bucket number 1 in big O of 1 time as demanded. This requirement is honored with our algorithm. But before the customer walks away, the customer looks at the board, number 3, and that number is copied onto the cheat sheet of that bucket that goes onto the bottom of this bucket. So instead of number 2, now the cheat sheet of this bucket says what? It says 3. This number is 3. So this link, instead of pointing to the bucket number 2, now points to the bucket number 3. Look at this, number 3, like so. Now the customer erases number 3, puts the number 1 onto the big board, walks away. Everything is happy. Now let's quickly examine the state of our linked list, or the state of our bucket list. The head of this list is what? Is this element right here, this node in the list, if you will. So 1 points to 5, points to 3. This is the number 3. 1 points to 3. 3 points to 5 over here. 5 points to 6. 6 points to null. Everything is good. Now let's pretend no customers walk into the door. And again, at this point, I'm not sure which one is more inconvenient. What is more inconvenient number? Let's say 4. Let's say 4. So the customer who grabbed the pen from the bucket number 4 is done. He or she walks up to that bucket in big O of 1 time as demanded. And what is the sequence of steps over here? This customer looks at the board. The number on the board is 1. So at the bottom of this bucket, there goes a cheat sheet with what number on it? Instead of 5, this number is now 1. This number is now 1. So the yellow arrow that models our pointers now points to what? This guy points to the number 1, points over here. This is where it points. So what is the state of our end obviously the customer erases number 1, puts number 4 on the board, walks away from the bank. And what is the state of our list? Well, the head of our list is the bucket number 4. 4 points to 1, boom. 1 points to 3, boom. 3 points to 5, 5 to 6, 6 to null. No more pens. Isn't that wonderful? And you can play out different scenarios in our format. I cannot really take input from you guys in real time, but let's say at this point, what happens? The customer number, let's come up with another inconvenient number. The customer number 0 is done, let's say. The customer number 0 is done, puts the pen into the bucket number 0. Again, the customer zoomed in on the bucket in the big O of 1 time. This is still the resource acquisition is done in big O of 1 time as demanded. So we honor that requirement. What number goes onto the cheat sheet of this bucket? The number that goes on the piece of paper that dwells at the bottom of this bucket is a number on the board. So now it's 4. So this link, instead of pointing to 1, now this link points to, where is number 4? Points to number 4 right here. On the board, we erase number 4. It was memorialized in the piece of paper over here, but what number goes here? 0, exactly. So what is the state of our linked list right now? Bucket list. Well, the head of the list is the bucket number 0. 0 points to 4, 4 points to 1, 1 points to 3, 3 to 5, 5 to 6, 6 to null. You see how this works? So now that you begin understanding the beat and the flow of this wonderful computer science data structure and our computer science algorithm tandem, you can already play out different games. Again, I'm all in favor of visualizing the way these algorithms work. I have only 2 hands and only 24 hours in a day. I cannot do it, but there will be a wonderful computer science project to actually animate this and take random input to see how this links dance within this memory box called an array. Now, in computer science, there exists an algorithm that is called precisely that, dancing links, but it was invented by 2 people, one Japanese, one American, and it deals with the game of Sudoku. But here we can say that links precisely dance because they are within the confines of a memory box called an array. So at this point, let's pretend that the customer arrives while these guys were filling out their paperwork. Now, boom, all of a sudden the customer arrived. What will happen? What's the scenario here? Well, the customer will approach the bucket with the pen in it in what time? Again, big O of 1 time, because this number is written on the board. So the customer comes to the bucket number 0, grabs the pen is gone from here. Now what the customer do before he or she walks away? Look at the bottom of this bucket, look at the cheat sheet. The cheat sheet says what? The cheat sheet says 4. So here the number 4 is copied. See, number 4 goes on the list. And at this point, where is the head of our bucket list? Well, now it moved to the bucket number 4. So 4 points to 1, 1 to 3, 3 to 5, 5 to 6, 6 to null. And this is how, again, this is how these links keep on dancing within the memory box called an array. Absolutely wonderful. Again, if something is not clear, use the comment section to ask your question. I try to explain things as simple as possible, but not simpler, in a very thorough way. But now, if maybe you can rewind and watch this little segment a couple times. I also suggest that you play with these scenarios on your own, come up with a differently sized bucket list and give it different scenarios. Draw the links on paper. That is perfectly fine. This is how you come up with the real life analogy of an algorithm, and then you will translate this algorithm into the best programming language of all times, C. In the comment section to this episode, there will be 2 links to 2 different files that capture the ideas that we discussed in this episode. The first file will be the _LL for linked list, which implements precisely this code that you see on the board behind me. And the second file will be called multi-threaded queue, empty queue, because in this file I implement a very straightforward thread safe queue that is based on the ideas that we discussed in this episode, a queue whose elements live in an array. This is how it's done, but this is a simplistic implementation of the ideas that we discussed in this episode. And for a true reflection of these ideas that we discussed in this episode, we will dedicate a separate episode. It will be the next computer science problem, not the next episode on this channel, but the next computer science problem, the computer science CS11 for season 3. Will be precisely that. It will be the objective of that problem will be to implement the ideas that we discussed in this episode in their true spirit as a linked list whose memory store is backed by an array, and within that linked list we need to implement a thread safe blocking queue, which means that when there are no more elements in this list or in this array, the queue is supposed to be expected to be blocked for as long as there are no elements in this queue or in this list. And conversely, when we try to add more elements to this list and the list is full, we're supposed to be blocked too. So here is the very basic no thread safe mechanism at all. Just an idea to give you an idea of how we convert the model that we set up, the real life model, into the corresponding computer science algorithm. Again, we understand that a computer science algorithm and its implementation in the host programming language are two completely different entities. And of course, I'm using the best programming language of all times, C. As a joke, you can implement your computer science algorithm in any language. C is my favorite language, so here how we do it. Again, I'm not going too pedantic on the signatures, the return values, and this and that. You can see all of this information in these free files. Just click on the link, pop them open in the separate tab, and there you go. Perhaps it's a good idea for you to do it now so you can tag along as I explain this idea. So in the very first linked list file, we define our structure to be a self-referential structure with the next three nodes, some data. Again, here is your opportunity to insert your data. Perhaps here you will have another very tall structure that will be your data, but the idea is this. We allocate a store, again, depending on how you want to do it. You can allocate it on the frame, you can allocate it in the data segment, store it as a global variable. Here is a sample allocation, calloc, that size, that many elements, and is the size of your array. Then our global variable, G is for global, first free node initialized to exactly, remember, this is what the clerk did with the big sign when prior to opening the doors of the bank for business. We put big fat 0 on the sign in front of our tables. This is how we initialize this list, and then the entire store initialized as follows, where we vary the index I from 0 to 1 less than the number of elements in this array. We say that the next free pointer points to the next element in the array I plus 1. And that means that by the time we're done iterating over this array, I is strictly less than n minus 1. It means that the last element in the array, remember in our real life demonstration, that was the bucket number 6, it must be pointing to where? To null, no more shared resources. This is how we do it with a dedicated line, return n for the number of elements that we initialized in that store. Because again, this bucket list, a linked list backed by an array, can play the role of a poor man memory allocator, for example. That is why my terminology over here, store, allocate, store free. When we allocate a node, we first initialize it to null, then we see if there is a first free node available, not null. We say that the free node is equal precisely to that. But then look at this. We set this free node to the just allocated node next free. So for example, if the free node happened to be the bucket number 6, remember the bucket number 6 pointed to where? To null. So this pointer will be null, and the next free node will say null, no more, and this is how these things work. Again, you can optimize the if statements. We return the free node. You can play games with this structure of the if statements. Maybe you can move something out, but essentially, fundamentally, without getting too fancy, this is what it is. And then we return the free node to the caller. Now, when we return this node to the wild, that node is used for a random and totally unpredictable amount of time, whatever it is, non-deterministic. But when this node returns from the wild into our store, we take it in as a pointer too. So here is basically a two-liner. How do we free a pointer, or how do we put it back into our store? Well, the node next free element, this guy right here, this member, points to where? Remember, this line right here, this line is the equivalent of the customer looking down in the bucket and looking at the number that is on the cheat sheet and putting that number from the sign into the cheat sheet. So that's what we say. Next free, arrow next free, is the first free node. And then what is this line? Well, this line is equivalent of the customer walking out of the bank and writing the number of the bucket on the big sign. The first free node is precisely that node that we just released, and this is it. Game over. You can look at the second file that I put together for you as a sample implementation of a thread save queue backed by an array on your own. Maybe I will mention a few words about that file, about this code, in the next computer science problem when we will have a dedicated episode. But as a friendly reminder, or as a heads up, the next computer science problem will be to take these ideas and wrap them into a thread safe code. So in that code, in that episode, there will be quite a bit of code. We will spend most of the time talking about this code. And in this code, I will use two primitives. It will be pthread mutex t, and then the other one, it will be pthread condition t. So with these two variables, mutex and condition variable, we will implement everything that needs to be implemented in order to wrap or flip or convert these ideas into a thread safe code. But for now, this is it with the computer science problem S3CS10, and we will move on to a new challenge next. Very good. Our next challenge will be a problem in mathematics, S3M24, the problem number 24 in season 3, and the objective of this problem is the following. Find all and only those complex numbers z such that they satisfy the equation that is written on top of the board. Z times z is equal to conjugate image of z. Z is a complex number, comes from the field of complex numbers. Again, nobody in the mathematical community cares deeply about the answers, but everyone answers to this particular problem, but everyone in the mathematical community cares deeply about your ability to come up with a story behind why all and only complex numbers such that they are what they are. And the title of the next episode, in which I will discuss my solution of this problem, will be There is More to Mathematics Than Meets the Eye. This will be hint number 1 for you. And the hint number 2 is that from my personal experience on Quora, for example, I see time and again, many students manage to accomplish the following two things when they solve this type of problem. First, they produce the correct answer. They do produce all and only numbers that satisfy this particular equation, but they do so in a not mature enough way. In other words, a more mature, mathematically inclined thinker will solve this problem not in a way which you will solve it with all due respect. And this is the hint, and this is the idea. Try to think on your own what is going on over here. And again, as another suggestion, if you think you solve this problem, think again. Now, this is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present my solution of the mathematical problem S3M24.